Okay, so as requested, I promised that I would do a UV-Vis matrix problem from beginning to end, giving you some real numbers, plugging those numbers into the matrix, and solving for the matrix all over. Because some of you are really having some trouble understanding what numbers go where and which ones I should use and how should I order it. And hopefully this video will help those types of problems that begin to happen. So this is very similar to your chrome and your manganese lab that you're doing. Chrome and manganese was a mixture, and it's up to you to figure out what concentrations of chromium and what concentrations are manganese inside of that mixture or inside of that sample of the unknown. But this one doesn't involve chromium and manganese. This one's going to be involving titanium and vanadium. So very often, like we've discussed before, in the transition elements, these are the elements that give you these wonderful colors that we can play off of in the visible spectrum. Chromium is listed in the transitions, manganese is listed in transitions, titanium and vanadium are listed in transitions, so they probably give us some type of colored solution. But I need to forewarn you that this is not the only area that we can do UV-Vis spectroscopy on a mixture with. We can actually go into the UV range as well to do it. So that basically means that I could take maybe something like a benzoic acid and caffeine sample, and I could have benzoic acid and I could have caffeine both inside of the flask. They're colorless, but I will be able to scan them in the UV range, and the UV range will give me the same type of data, and I can do the same type of matrix. So don't get comfortable with the idea that you can only do these types of problems using colored solutions, because that just simply is not the case. Okay, so titanium. What about titanium that we need to know? Okay, well, titanium is a transition metal, and titanium 3 complexes can give us beautiful kind of purple-violet colors like you're seeing here in the picture. It's also, for those of you who are inorganic, it's also very common in the organometallic reactions now. So there's a lot of different types of studies and a lot of research and development that's going on with our titanium solutions. So I'm just going to kind of color this in a little purple. So that's our titanium, and I'll mention this again before we start the problem, but we're going to be doing some little bit of grunt work beforehand, and we're going to be providing you these numbers, and I'll mention that again in a minute. But this is our titanium standard. So this is a purple solution. It is titanium, and now we need to look at our vanadium standard. So what does vanadium look like? Well, vanadium is one of these very nice transition metals that we don't really speak that often of, but these are the different colors that vanadium can come in. So depending on the valence state, the charge that's up at the top, we can get anything from lilac color to a beautiful emerald green color to basically a sky blue color to a yellow. So I'm just going to say, well, we're going to pretend in this example problem we are going to be using the vanadium 3 complex, and that's a green color. So I'm going to go ahead and put in green for vanadium. It could have been either one, depending on which one I chose, but there we go. Okay, so we've got these two standards now. Now, before we actually got these numbers, what we did is that we ran titanium standard and got some data. And we put titanium in the UV-Vis. And what happened with this titanium is that we got a spectra. Okay, and the spectra maybe looks something like this. Okay, for titanium. So what we do is that we go and we take a look at the UV-Vis spectra of it. Okay, so let me scroll back up. This is giving me an issue this morning. Okay. So we go back up to the spec and we take a look at the lambda max, and we're going to pretend like this lambda max is at 390. So that's why we've kind of done this here. We've done titanium lambda max at 390 because that's where our peak was at. That's where we're actually seeing some of our data come into the picture. Okay, so after I've ran my titanium and I've got this spectra, I look at the hump and the peak is at 390, so here's 390. And then I don't really do anything else with titanium from that point except calculate a molar absorptivity. That's really all that I do. So let's pretend like we know the concentration of the titanium that we made standard wise. So I would put that into Beer's law, A equals EBC. So I know the absorbance that is given from the instrument. It will tell me that. I know the concentration that I made, and I'm going to be solving for molar absorptivity. And when I do that, 678 comes around. Okay, so at 390, this represents titanium's lambda max. And when I ran the standard and I calculated the molar absorptivity based on what I made, 678 is going to come from it. Okay, so there's one piece of the story that we've not done. And in another example that we'll do, I'll go ahead and I'll work through that part of the problem too. But for this one, we're going to pretend like a lot of this back work is done for us already. Okay, then I take my standard of vanadium. And what I begin to do here, and let me just do this in purple too. All right. Okay, so what I begin to do here is that I begin to run my vanadium, and I put the vanadium on the spec and I run it, and I might get a hump that looks something like this. Okay, so then I take a look at the lambda max, and that lambda max is at 450. Okay, so that's where this number came from. This is a lambda max at 450. So that represents vanadium's maximum absorbance. That's the wavelength where we get the maximum absorbance from it. Okay. So once these go into the pitcher, I do the same thing there. I know the concentration of vanadium that I made. This concentration of vanadium goes into Beer's law. I know the absorbance that that standard would give me. I solve for molar absorptivity, and when I do all of that grunt work, I get 279 for the molar absorptivity. Okay, now, because we get two different components, we have to understand that we have now a mixture. And this mixture in this flask is going to be made up of a little bit of titanium, and it's going to be made up of a little bit of vanadium. And it's our job to figure out how much of each, right? We got to know how much of titanium is in there, we have to know how much vanadium is in there, and then not only that, but we have to understand that this mixture with the two components, the absorbances from these mixtures are basically due to titanium absorbance and vanadium absorbance both. So we call that additive. Okay, so I take this mixture just like you did in your lab, and then what you do is that, okay, titanium absorbed at 390, so I'm going to run this mixture at 390, and that's what we get here, and I get an absorbance of a 0.651. And then the other piece is vanadium. So I take this unknown mixture and I run it at vanadium's wavelength at 450, and I get another absorbance, 0.547. Well, this 0.651, part of that comes from the titanium absorbing, and another part of that comes from the vanadium absorbing. The same thing is happening at 450. A part of that, the 0.547, a part of that absorbance is coming from titanium, and a part of that absorbance is coming from the vanadium. And it's up to me to figure out how much of it is contributing to titanium and how much of it's contributing to vanadium. And that's the whole point of your chromium manganese lab, and that's the whole point of this problem. So in order to do that, we have two unknowns and two concentrations to solve for. We need to use a matrix, and this is the matrix setup down here at the bottom, right here. So this is to solve for the X component, and this is to solve for the Y component. That can be found in your PowerPoint. So on the PowerPoint, probably on the very last page of the PowerPoint, if this ever decides to load up for me, you will see the matrix equations listed, and they will be there for your review. So you will see the same exact matrix setups. The only issue is that some people are not very comfortable with how to solve for these matrices, and that's what we're going to work through step by step throughout this problem. So maybe not the last slide, but a couple of slides before the end, you will see this PowerPoint sheet, and it will give you two different types of matrices here. One of them will concern solving for the x component, and here they are. And the other one's going to be solving for the y component, and there's that one. Okay, so the deal here is that in my version, I leave off the b's. And the reason I leave off the b's is because it makes the matrix look a little bit better. But most of the time we're assuming it's a 1 centimeter cuvette. And I don't need to be putting ones in here to solve for this problem, because anything multiplied by 1 is the same number. So that's the reason that I leave off the b's in my version of the actual matrices itself. So that's why when you see these matrices here that are written, they look a little bit simpler, at least, because I'm leaving the b's off. All the problems that I will give you, especially concerning the matrix, will be assumed to be in a 1 centimeter cuvette. Okay, so stay tuned. In the next video, we're actually going to start plugging in numbers and